So my motivation and objectives for this talk are firstly to extract information about lunar exospheric dust dynamics using the abundances retrieved from the Apollo coronal photographs of lunar horizon glow, the ones that Dave discussed earlier on. Okay, so once I've done that, then the interesting thing would be to compare with dust motion observed with LEAM to see if it seems consistent. And then once we've done that, then we can kind of determine the dust flux from the surface, and then we can ascertain whether or not that dust flux is consistent with the retroreflectors being coated with dust. And then we can briefly sort of assess some of the wider implications of that dust transport. Okay, so all right, trying to get comfortable with this. All right. Okay, so these are some of the results that Dave talked about earlier on. So he didn't actually show this, but he actually produced a 2D map of the high altitude dust concentration above the sunrise terminator using data from Apollo 15 coronal photographs. Now, this map and these concentrations here are assuming that the dust grains have a radius of 0.1 micron. Okay. Now, although we didn't look at very many photographic sequences, there seemed to be a hint that this high altitude dust was possibly more abundant at sunrise than sunset. That's sunrise and sunset at the surface. I mention that because Apollo was in a retrograde orbit, and so orbital sunrise was above sunset and so on. It's a bit annoying. And also what we found was there was no apparent correlation between this lunar horizon glow and solar wind conditions or solar UV conditions. And if electrostatic dust transport is causing this dust at high altitude, you'd expect some kind of correlation. And for this limited number of events, there wasn't any. So that was a little bit puzzling. And so there did seem to be a correlation with meteoroid streams. And I think this particular event, the Apollo 15 sequence, coincided with the southern delta asteroids stream. And so then we proposed, sort of speculated, that there could be some sort of saltation-like cascade process, which would be initiated by impacts, and then the debris from those impacts would come back down, hit the surface, knock out some more dust, and so what that would do, it would decrease the velocity of the dust, but increase the concentration potentially. So we speculated that might be a process that was happening, and so kind of like a third mechanism, I guess. And okay, and I just might have mentioned in this plot here, you see that the dust concentration seems to be increasing maybe towards the day side. You know, if you kind of extrapolated these lines, this does hint that maybe the dust population does extend beyond the terminator a little ways. Okay, so that was the data set I started with. And so in order to infer some dust dynamics, a neat thing to have is a velocity distribution function, because once you have that, you can then take moments and do all sorts of neat things with in order to infer dynamics. And so I kind of try to keep it simple, so I just assume that dust grains at high altitudes are on these sort of random ballistic trajectories, and then you can kind of use the sort of following expression, and it kind of is analogous to a Maxwellian, essentially. And so you've got the variables we use here are dust concentration at the surface, the velocity vector of the dust grains, and then sort of have a characteristic velocity, which is kind of analogous to temperature, and then we have lunar gravity and height, these in there, which is sort of decreases the energy of the dust grains. So then if you assume that the characteristic velocity is going to be a lot less than the escape velocity, which is a pretty reasonable thing to do, then you can derive an expression for dust concentration as a function of altitude. And you can see this sort of exponential form looks pretty familiar. So basically, the dust scale height tells you about the characteristic velocity, if you know what gravity is, and which you do. So this is a neat way of being able to extract information from that data. And so this is what I did. So this is one cut from Glenart et al., one of the retrievals. And this is for T minus 17 seconds. So that's 17 seconds before orbital sunset. Yep. And so this is the closest picture taken to orbital sunset. And the fit was assuming that the dust grains are 0.1 microns in radius. And you can see that once you get above 20 or so kilometers in altitude, the uncertainties get pretty huge. But certainly close to the surface, you know, it kind of does a pretty good job there. So the black dots are the retrieved data. So then if I fit the distribution function, the moments that I was talking about earlier on, I actually found that you get a good fit to that line if you use 3 separate distributions. So you can have a low energy one here in the red, a mid a mid altitude one in the blue, and a high altitude one which is the black line. And together they produce a sort of green dash curve, which actually does a pretty good job. And so the fact you got 3 scale heights there, it could tell you something about some of the mechanisms that are at work. Okay, and so these are some of the values that we extracted from those fits. And so obviously the concentration kind of matches up with what they found. So you find the low altitude population has a scale height of about 1.5 kilometers, mid altitude 8.5 kilometers, and then 50 kilometers for the high altitudes. And this correlates, relates to characteristic velocities of about 69, about 70 meters per second, 150-ish meters per second, and 400 meters per second. And so kind of what does that tell you? So the multiple scale height seems to be consistent with this cascade, the cascade expected for a siltation-like mechanism, but it could also hint at different transport mechanisms dominating in different altitude ranges. So for example, the low altitude dust could perhaps be mostly levitating dust, or actually probably more likely mostly lofting dust. And so that would kind of maybe match reasonably well with the dust fountain model, which does struggle to get dust up to tens of kilometers. Okay, and then the characteristic velocities are consistent with what was found for LEAM. So depending on which study you look at, you know, it's either around 100 meters per second or less than 1,000 meters per second. And so the speed seemed to be consistent. Although the dust striking LEAM is consistent with those dust grains being much bigger. And so, but certainly you'd expect them to, the characteristic speeds we infer here to be kind of roughly in the same ballpark. Okay, so then ever so quickly, just looking at the influence of grain size on dynamic properties. So the shape of the retrieved profiles are going to be independent of grain radius. So the scale height and the characteristic velocity will be the same whatever grain size you choose. And basically here in this table, I just look at the bottom line here, total concentrations at the surface, and you can see that small changes in the assumed grain radius gives like massive differences in the total concentration. But we pretty much knew this already because that's a consequence of how you do the scattering inversion. Okay, so then the next thing we want to do is to be able to infer dust flux from the surface. And so using the same process as before, we can just get this very simple expression here for the flux of dust either going, leaving the surface or returning, assuming that none of it's lost. Okay, so when we do that, if we just look at this bottom line, we get dust fluxes of millions of dust grains per meter squared per second. Okay, and that's just for a 0.1 micron grain. But even for a 0.3 micron grain, it's still sort of 10 to the 4. So that's pretty huge. But of course, you've got to think about what the mass flux is. And so that's at about, for the 0.1 micron case, that's about a nanogram per meter squared per second. So even though the number of fluxes look huge, the actual mass fluxes, the mass that's being moved around is actually pretty minuscule. Okay, so then another question would be, so if you have a planar surface on the moon, how long does it take for it to get completely coated in dust, based on this mechanism? Okay, and so we're just considering the downgoing flux, and we're assuming that all the dust that hits the planar surface, it all gets stuck. So it's a very, very simple calculation. And this isn't too bad an assumption because fine dust is very adhesive, so this is kind of very reasonable to assume it'll probably get stuck. Okay, so based on the fluxes I just inferred a minute ago, the minimum time for total coverage of a surface would be about 152 Earth days. So that's really not very long at all. And the mass of dust of a dust monolayer would only, for 0.1 micron grains, would only be about a third of a gram. So really, for a square meter, for total coverage, that's only a third of a gram. That's hardly anything. And even if you look at the bigger dust grains up at 0.3, that's only a gram of material would totally coat a square meter. And so these timescales here are very quick on geological timescales, and not much mass is required to do coating. And so then, of course, that leads into the retroreflectors. So what about those? Well, a recent study by Tom Murphy reported that the number of laser-ranging photons returned from the Apollo 15 retroreflector was about a factor of 10 less than he'd expect. Okay, thank you. Okay, so such a decrease would require about 68% dust coverage, and that would have had to have occurred over about 35 years or 470 lunations. And so, so the minimum time to cover 68%, say for a 0.1 micron gain, is about 104, Earth days. And so the minimum fraction of each lunation required to reach that over 470 lunations is only about 0.008 of a lunation, which corresponds to a longitudinal extent each orbit of having active dust transport of about 3 degrees. So that's really not much. So basically, it appears to be quite plausible that there's enough dust to have coated these retroreflectors. So in that case, why aren't they totally obscured? Why are you getting any returns at all if there's that much dust flying around? Well, in these simple calculations, I've assumed that all the dust sticks and it's coated evenly across the reflectors, and that almost certainly does not happen. And so in this saltation-like process, which we've been discussing, dust striking the retroreflectors will sometimes hit dust already there and possibly knock it off. And so then you'd expect maybe this process to reach some sort of steady state, so that on average, for every dust grain that's lost, for every dust grain acquired, one is lost. And perhaps this kind of steady state is reached when you get about 68% coverage. I mean, that would kind of fit with what we're seeing with the retroreflectors. And of course, because of the limitations of this retrieval, we haven't considered the larger dust grains. We can only really say something about the submicron stuff. And so this dust coating process is perhaps something of a statistical process. So then, in that case, why aren't ejector rays and other surface features obscured by this process? Well, in the calculations I did a second ago, I was assuming a planar surface, and the lunar regolith is not a planar surface. In fact, it's very much not a planar surface. So it's a very porous surface with sort of a very fractal nature to it, and this means that it actually has an immense surface area. So there's a lot of the cross section for the dust to hit is absolutely massive. Is many orders of magnitude bigger than just a nice smooth flat plane surface. And so you'd expect any obscuration by this process to take a lot longer for the regolith in general. Okay, so a quick summary. So we've looked at the sunrise dust dynamics from Apollo 15, assuming random ballistic trajectories. The multiple scale heights could hint at a cascade-type saltation-like process and or different transport processes at different altitudes. The characteristic dust velocities are consistent with LEAM. The derived number fluxes are huge, 10 to the 6 per meter squared per second, but the mass fluxes are pretty tiny, at about 10 nanograms per meter squared per second. And these dust dynamics occurring over 470 odd lunations could explain the factor of 10 drop in the return photons from the retroreflectors. But this process would be much less effective at obscuring surface features. Okay, done. Yep.
Hi, I'm Phil Metzger from Kennedy Space Center. First question is, so the dust is leaving the surface by photoionization?
No, I didn't say no.
Okay, it's solar wind, but whatever. Anyways, it's leaving the surface. So the same mechanism could also cause it to leave the corner reflectors, right?
That's exactly what I was saying. So in my very simple calculation, I assumed that it was only accumulating dust. But if you remember, I kind of invoked this saltation-like mechanism. So the retroreflector could reach a steady state where it accumulates. Whereas, for the dust it accumulates, it also loses dust because dust gets knocked off.
But not just knocking off, but the same mechanism that removes it from the surface of the moon should also remove it from the surface of the reflectors. And I'm wondering if the electromagnetic environment on the retroreflectors would be different than the lunar surface because of the material differences.
Yeah, it would be different because it's glass and metal, whereas regolith is made up of different stuff.
Okay.
Okay, we have time for a quick question. Brian O'Brien. Tim, could you flash up the slide of the deposition, please? Number of milligrams per square centimetre and so on.
Okay.
The table.
Yeah, this one?
No, you got a table of that one, yeah.
Okay.
So you've got, in a few days, well, the Apollo 12 dust detector has got a horizontal solar cell and an east-facing vertical one, west-facing, and it decreases by about, it would decrease by about 10% or half a milligram. Oh, you're into grams there.
Yeah.
Okay, I need to do some numbers.
Okay, yeah, I mean...
I'll get you the answer fairly quickly.
Okay, I mean...
Over 5 years.
All right, this is the time, assuming that the flux was continuous. Obviously, it's not going to be continuous all the time. There are going to be points in the lunation where you get dust transport and other times you don't. And this number here is just saying that's the mass of dust that would, cover a planar surface with a monolayer. So my point there was you don't need much mass of dust to obscure a surface. It's a very small amount. Okay.
Okay, thank you.